All right, guys, I am very excited to start chapter 1 with you. What I call chapter 0, right, is mostly review. And now we're entering the real heart of the course. Okay, we're going to talk about quadratic equations. So going from boring linear stuff with just an x to adding that x squared, making it a quadratic and seeing what happens. We're going to start today in this video talking about just standard form, and I'll go through one or two examples. Okay, I'll probably do another video with just another example, and then we'll move forward into other forms from there. Okay, so what makes a quadratic a quadratic? It's adding this degree. So we're leaving the linear world behind where it's just x plus a constant. We're adding this right here. Okay, now this is going to create a very unique shape called a parabola. Okay, a parabola is, as you can see here, a curve where any point has a mirror point across from the axis of symmetry except for the vertex, which is on that axis. So it's a lot of vocab words that I just threw at you. Right? I want you to think about why the parabola happens. I think that's as important as understanding like how to actually graph this. Like, why does the parabola occur? It's because I've added this right here. Because when you square a positive or a negative, you'll get the same result, right? Negative 3 squared is 9, and positive 3 squared is 9. So it makes sense that you could have this point that's over at negative 3 and up at 9, and over at positive 3 and up at 9, right? All parabolas will be full of these mirrored points across the way, except for the vertex. The vertex will be this one lonely point that represents either the maximum value or the minimum value of the parabola. Right? So if we think about where this comes from, it's this idea that there is going to be some number that you input into the function that only results in one output, and it will only happen one time. The simplest example of this is if it's just the equation y equals x squared, our base model, right, that I was sort of just talking about earlier, that if I did negative 3 squared, I'd get 9. If I did 3 squared, I'd get 9. Well, if I did 0 squared, I just get 0. And there is no such thing as positive or negative 0, right? So we'll talk more about this later, but I think it's just important for you to know, like, why does a vertex occur? There's always going to be something that only happens just once, all right? And that place where it happens just once is also going to be a good indicator of where our axis of symmetry is, right? Think about what it means to be symmetrical, right? That's going to apply to parabolas, that anything on one side has to be perfectly mirrored on the other, where that distance is congruent to that distance, where they're the same distance away from that perfect middle line that sort of cuts it into two pieces. Right, so I believe the next slide is sort of a review of some of this. Okay, right? Like I said, vertex also going to be called either the maximum or the minimum. I mean, I personally go with vertex because it applies to either situation, right? Minimum only occurs if it's concave up like this, and maximum only occurs if it's facing down like this. The axis of symmetry is a vertical line, so it's important to remember it's always written as x equals something, because what does every point on this dashed line have in common? It's at the same horizontal position. I can go up or down it as much as I want. And the vertex, like we said, is always going to be somewhere on that line. It's always going to be on that line. So let's talk about standard form. Like, what do these normally look like, and how do we use this form to evaluate graphs and to create graphs on our own? Okay. First of all, A, the leading coefficient. Why is it important? Well, that's going to determine if we have a maximum or a minimum, right? That this is an example of something with a positive leading coefficient. This is an example of something with a negative leading coefficient. Okay? If this is negative, we know that it opens down, that it's going to result in there being this maximum point and everything else just careens downwards. C is important because just like in y equals mx plus b, there is this constant here at the end, and that constant is absolutely the y-intercept. Why do we know this? Well, because just like in y equals mx plus b, when you plug in a 0 for x, meaning you're going to be on that y-axis, all that's left is the constant term. Well, same thing here. I've added another variable with another degree, but if I plug in 0 here, it goes away, there's nothing. If I plug in 0 here, it goes away, there's nothing, and all I'm left with is negative 14. So that is still going to help us find a y-intercept. The most important piece of the standard form is this little mini formula, negative b over 2a. So taking the negative of that middle term and dividing it by doubling the leading coefficient. And where that will tell you is the perfect axis of symmetry. It's a short little formula that works perfectly every time to give you the x equals blank, that vertical line. And that's awesome because not all these parabolas are very centered on our graph. So we need to know where is the middle, because then I can start to plug in values on either side to sort of like flesh out the graph and see how the rest of it looks. Okay. We can then use this information to find the vertex, because if negative b over 2a gives you the x value of the vertex, because it has to be somewhere on this line, right? See, here's the vertex, has to be on the dashed line. Then I can just plug that value in, and that's how I can solve for y. So let's start actually doing that and see how this works, okay? So if I look here at this equation, the first thing that I need to do, can't do anything else until you do this, is figure out negative b over 2a. It's the first thing we need to do. So in this problem, that's going to be negative 2. It was originally positive, but I'm making it negative. Divided by 2 times a. If there's nothing here, it implies that there's a 1 there. So 2 times 1 is just 2. So here's what I've learned. X equals negative 1. That's the axis of symmetry. So there's this invisible line, so I always draw it as like dashed, because it's not really there, but we want to know that it's the midway point. That this is going to split the graph into its 2 symmetrical pieces. And somewhere on this line is the vertex. I don't know where, but I do know this. I do know that it will have an x value of negative 1. So why don't I take that negative 1 and why don't I plug it into the equation? So y needs to equal whatever happens when I input negative 1. So negative 1 squared, this is where parentheses become very important. Negative 1 squared plus 2 times negative 1 plus 2. So negative 1 squared, that's positive 1. 2 times negative 1 is negative 2. And then plus 2. Well, negative 2 plus 2 is 0, and then I just have 1. So what does this tell me? Negative 1, 1. That's my vertex. From here, everywhere you go from here, I'm going to change my color there. Everywhere you go from here is going to have a mirror. This point exists on its own, but if I decide that I want to plug in points and go this way, I can just copy all those to the other side. If I decide I want to move this way, I can copy all those to the other side, right? But why don't I move in this direction? Because I think 0 is a pretty easy one for me to find. Why? Because we agreed 0 helps me find the y-intercept. If this is 0, it cancels. If this is 0, it cancels, and I'm just left with 2. So 0, 2. Right, now, if this is the case, if this is really true, all right, then when I plug in negative 2, I should be guaranteed to get 2 as well. Should be guaranteed to get 2 as well. Well, let's see really quickly if that works. What's negative 2 squared? It's positive 4. What's 2 times negative 2? It's negative 4. And 4 minus 4 is 0, plus 2 is 2. So look at that. I'm not lying. This works, right? But I would say that this maybe seems like a little extra effort. If you can figure out that the change that I had to go in this direction was 1, and that the change I had to go in this direction was also 1. I might have subtracted 1, but the actual change was 1, right? The distance from the axis of symmetry is just 1. Then I don't really need to plug this in. I can be clever, right? We're not trying to be lazy. I'm saying let's be clever. Let's use our logic. So let me move this way and see what happens if I do 1. What happens if I plug in 1? Okay. So if I plug in 1, 1 squared is 1. 2 times 1 is 2 plus 2. So 1 plus 4, which is 5. So 1, 5. I do not need to confirm that if I'm 1, 2 away, then I can go 1, 2 away, and I'll be at 5. That's a guarantee. It's a lock. And then I can piece these together, and I've got a parabola. All right. So there's your example for how to get through one of these. All right, I'll probably do a separate video for one where we are concave down. All right, as another practice. But this is our day 1 introduction to what does it mean to graph these things, an understanding of what does the equation look like, how do I use the equation to create a graph.